Hello and welcome to Carlum Cymru e-sgol sessions. My name is Mr. Ridd. I'm from Comfort Comprehensive School in Bridgend, and today I'm going to be taking you through A2 Unit 3 Oscillations and Nuclei. We're going to look at the 2017 paper, and with the help of my colleague Jane Owen from Penglai School, we are hoping to get through, well, as many questions as possible. So let's get on with it. So we make that progress. Now, number one, describe an experiment that uses various absorbers to identify the types of radiations emitted by a radioactive sample. Justify all steps in the experiment. Sometimes a question might, and it's worth just remembering, ask you to use magnetic and electric fields as a means and a mechanism to identify different types of radiation. So just be aware of that method as well. When it comes to absorbers, I'll draw the diagram. We're going to need our source, okay? Our source. We will then need some absorber or absorbers. And we're going to need some kind of detector or GM2. Now, I think you should spend more time on your diagram, possibly use a pencil and a ruler, but we're just for the purposes of showing you, this will do just fine. Now, if we have an unknown source, we have to consider the penetrative properties of alpha, beta, and gamma radiation as a means to figuring out what we've got. But before we do any of that, we have got to make sure we take note of the background radiation count, the ambient radiation that's present in whatever room or setting that we're in. So initially we would do this, take a background radiation reading with the source not present more than 2 meters away. Once we do that, and we do that by measuring the count rate over maybe 5 minutes, and then we put our source in front of the absorbers. Now, alpha, if it is present, will be stopped by something as thin as paper. So by putting a absorber as thin as a sheet of paper between source and the detector, we should see a reduction in the count rate. If there is no such reduction, that means that it is likely not an alpha source. Then we change our absorber. We change it to maybe aluminium, which is a few millimeters thick, sorry. And then if we put our source in front of that absorber, our aluminium, and we see a reduction in the count rate, then we'd know that we were dealing with a beta source. However, if we still saw after that, though, that our count rate was a little bit higher than our background radiation, it would mean that gamma radiations is also present. Now, this is all written here. You can pause it. Everything I've just said, I've just explained it, but feel free to pause the video and have a look at that explanation written down there. I'm not going to waste time going through and writing that when it's just off to the side there. Okay. So, a radioactive sample of material has a half-life of 11.4 days and an initial activity A0. Determine the decay constant. Now, to determine the decay constant, we'll use this relationship. Lambda is equal to ln2 over T half. Incidentally, you may need to derive this relationship. That's another question for another time, but something to be aware of. Now, I personally prefer to convert things to seconds just to be on the safe side, and I tend to like to work in meters, kilograms, seconds when I'm doing my calculations, so I don't forget about these things later on. So we've got T half then, which is going to be 11.4 in seconds times 24 times 60 times 60. And if we put all that in, we end up with 7.037 times 10 to the minus 7 seconds to the -1. Unit 4, the decay constant seconds to -1. Remember, it is the probability of decay each second. Probability of decay each second, which in this case, of course, is relatively low, I suppose. 7.037 times 10 to the -7. Next, what is the activity of the sample after 57 days? So a good way of doing this is to consider how many half-lives. How many T half? To work that out, we're going to need 57. We're going to divide that by the half-life, which is 11.4. And conveniently, that comes out as a nice round number of 5. So we've gone through 5 half-lives. Then we can use the activity. We can use this formula. A is equal to A0 divided by, now it's normally 2 to the x, okay, where x stands for the number of half-lives. So we're going to have A0 over 2 to the 5, which is essentially A0 over 32, where A0, of course, is our initial activity. All right. Now it's asking it for it's asking for the answer in terms of A0, and we have put it in terms of A0, so that's not a problem. The percentage decrease. Now that's really easy if we've done the last bit, because the percentage decrease in the number, because A is equal to lambda n, because the activity is linked and is directly proportional to the number, and we've got the constant in there, then after 57 days, the activity has gone down by a factor of 32. That will also mean then that the number of radioactive nuclei will have also gone down by a factor of 32. So we're able then to say that n is going to be equal to our initial number divided by a factor of 32. Now, 1 over 32 is equal to about 3%. We've got to be careful though, the percentage decrease, yeah, we've worked that out. Okay, the percentage decrease is going to be 3%. So we've actually done that question, and that's completed. Right,
Yeah,
moving on.
That'll give you 2 marks. So what we've got to do a percentage decrease, so you've got to take 3% away from
Oh, sorry, it'll go down to 3%. Sorry, you're absolutely right. So then we've got to think about if it goes down to 3%, sorry, after 57 days, then the percentage decrease is going to be 97% decrease. Right. Nuclear energy can be released by fusion or fission. Describe these processes by considering the graph of the binding energy per nucleon plotted against the nucleon number. Now, this is quite a hefty and common, I'd say, 6-mark question. Sometimes not, you know, it can be 4 marks, but they often ask you to write and explain what's going on here. In some questions, they've even asked you to sketch this graph as well. Now, importantly, I think you should consider labeling this up. So when you get the binding energy curve like this, I'd be labeling this as fusion, and then I'd be labeling this as fission. And in fusion, we are increasing the nucleon number. This is where lighter nuclei combine together to form heavier nuclei. When that happens, the mass decreases. There's what we call a mass defect. The mass goes down. The loss in mass then is released as energy, and that causes an increase in the binding energy that holds the nuclei together. Now, binding energy per nucleon as well is also a measure of stability. So to increase the binding energy per nucleon is to also increase the stability of the nuclei that we have. The same can be said for fission. Now, in the process of fission, we have heavier nuclei splitting to form lighter nuclei. When that happens, again, you can see on this curve here, we have an increase in the amount of binding energy per nucleon. There is a release of energy. Again, there's a mass defect, and that manifests itself as a release of energy. And then the other thing worth commenting on, really, I suppose, is the greatest stability of all, maybe this kind of region here, where you've got iron. Iron is probably the most stable, or close to the most stable nuclei that we know of. The binding energy per nucleon is at its highest. That all I've said, I'll leave it here. Okay, pause for you to maybe copy that down so you can see the model answer. All right. Right, the fusion of hydrogen into helium in the sun may be represented by this equation here. Calculate the energy released in mega electron volts. Right, so to complete this question, we have to remember that essentially the amount of energy on both sides must be conserved. So to begin with, what we're going to try and do is work out the mass defect, because when this fusion reaction happens, remember the mass of the helium nuclei is smaller than, if you like, the sum of its parts. So we'd expect to have a smaller mass on one side than the other. Let's work out what that mass defect is. Now, the mass defect is often annotated as delta M. And we say that delta M, or to work that out, then is going to be equal to 4. Now, if you look at this side here, we've got 4 times the mass of hydrogen, which is 1.00728. And then to add it to that, then we've got to add on the mass of these electrons, which is 2 times 0.00055. You have to be very careful with the significant figures that you use in these questions. You've got a lot of significant figures and you have to treat them with respect. So make sure you carry them through in your final answer. Now, that's the left-hand side then. And from that, we're going to subtract 4.00151, which is the mass of our helium nuclei, and work out the difference. Now, you might stop and think to yourself, well, what about these particles here, these electron neutrinos? We say that electron neutrinos have a negligible mass. We'll ignore their mass. We'll pretend they don't exist, okay? And then, so that mass defect then comes to 0.2871 atomic mass units, okay? Now, we have to remember that 1 atomic mass unit is the equivalent of 931 MeV, okay? That's a very helpful conversion because it makes the next part really quick. So if I do 0.02871 times 931, we end up with 26.7 MeV. And we finished that part of the question. Just scroll. Yes. Nuclear power has played a role in the generation of electricity in Wales. Wilfer, Newydd on Anglesey, close to where your neck of the woods, isn't it? May feature in future further developments indicate the benefit and an issue that may arise from such projects and discuss their relative importance. Okay, I am going to skip through this one because it's just something you're going to have to learn. And to be honest, though, it's Key Stage 4 physics. The idea that, of course, there's no CO2 emissions is going to bring jobs. But of course, downsides of radioactive power with power stations are the disposal of radioactive waste. So pause it, take a look. How am I doing for time? Have we got time to have a go at this question? I think we have, haven't we?
Yeah, you've got 5 minutes.
Yeah. Okay. So the first law of thermodynamics is given by delta U, which is, well, we'll talk about that now, is equal to Q minus W. So what is delta U? This is the increase or change in internal energy of a system. Remember to put the word system in here, otherwise you're going to lose marks. And then this is going to be Q, heat, flowing into the system or supplied into system. And then W is work done, and this is very important. This is work done by the system. Work done by the system. Now, work done by the system is a positive value. Work done on the system is a negative value. A fixed mass of gas is taken around the closed cycle A, B, C, A. Complete the table by describing each process in terms of pressure and volume. The description of process A to B is already inserted. Each process state if any work is done, and if so, indicate if it is done on or by the gas. No calculations are required. A to B then. If we look at A to B, first and important thing to note is that there is no change in volume. So if there's no change in volume, then work is neither done on or by the gas. And we'll make that note there now. So no change in volume, and work done, well, none. B to C. B to C, we can see that there is, if we describe it, there is a decrease in volume at constant pressure. So we'd say constant P, and there is a decrease in volume. Is work done on or by the gas? Right, well, if there's a decrease in pressure, sorry. If there is a decrease in volume, work is done on the gas. Work done on gas. And then C to A. Now with C to A, we've got a couple of things going on here. We've got, it's linear, okay? Linear decrease in pressure. Linear decrease in pressure. I'd write pressure down if I were you. I haven't got enough room though. With increase in volume. With increase in volume. Right. And now is work done on or by gas? This is work done by the gas because we've got an increase in volume. Okay, so this is work done by gas. Right. Determine the net work done on the gas during the entire cycle. Now the net work done here, C is going to be the work done, if you like, by the gas. So that's like the area underneath. C to A, sorry. So C to A, if I needed to work out the work done by the gas, then it would be all of this. The work done on the gas, though, from B to C, is everything under the line BC. And essentially, the difference between those two things is going to be the net work done on the gas. Now, that is the same as working out this area here. So the net work done is the area of that enclosed space. Now, I am not going to spend the time working out the area of that triangle. I think we'd better served if we just moved on. But one thing to note and to be very, very careful of is when you're working out the area of this triangle, you've got to make sure you take careful or pay careful attention to the units here. So this is pressure times 10 to the 5 newtons per meter squared. And then down the bottom here, we've got volume times 10 to the minus 3. So when you're working out your half base times height and you're working out those values, make sure that you pay attention to those, that standard form, because a lot of people miss it out. Now, if you do that and you give it a try yourself, you should come up with 200 joules. So that's a little exercise for you to try. it is the net work done, the area of enclosed space. Same mass of gas is taken around A, B, C, A for a second time. For this cycle, the temperature is kept constant between C and A. It's isothermic then. The new path from C to A is shown in red on the graph below, together with the original path. Show that the temperature is constant along the path C to A. Okay, so if it is isothermal, okay, it is isothermal, then that should mean, if you think about PV is equal to nRT, if T is constant in this situation, then P times V should equal a constant. Hence, any two values of P and V, so if I took like this value here, 1.8 times 10 to the 5, and that corresponds to a volume of around about, if I draw this on, look, we take that value, and that value for volume, multiplying those two values would give me a constant. And then if I was to do the same at any other point, so if I just arbitrarily chose another point, say here, and once again worked out what the pressure and the volume were just by reading it off the graph, multiplying those two values together will also, or should, give me the same number. So if it's an isothermal process, then P times V, any 2 points on that graph, should give you the same value. So again, I think, just to get through it, I think you can have a go at that and check, see whether or not that's correct. And then the last bit then, estimate the difference in the net work done in the two cycles. Well, you would have to work out the area underneath that curve, which can be a little bit tricky. Now, I would recommend looking for small squares maybe and counting the small squares to work out the difference, all right? And if you do that, you've just got to appreciate what one small square is worth. I'm very conscious of the time, and I know I'm cutting into yours now, Jane. So I'm going to leave it there, but I'm just going to finish by saying, to do this question effectively, you really need to think about what one tiny square is worth, and or do it in terms of maybe 1 centimeter square and think about how much energy that is indeed worth. Okay, and I'll leave it there.
And that's a really good graph skill to kind of, you know, that they've thrown in there. That
And it's a very tricky one as well.
Show. It is, but I think you've done it justice there. So, okay, if you stop sharing your screen, I'll share my screen first before I jump on.
There we are. I've left that answer just there for a moment, okay? So if anyone wants to pause that, and then they can have a look at that. That's done. So I'm just going to stop sharing now.
And all of these answers will be on the resource. Thank you, James, for the handover. And I'm switching over onto question 5 because that gives us circular motion, and that also gives us some valuable graph skills, which WJC are going to assume that you've had lots of practice with doing all of your practicals. And so let's go straight into it. You can read the question. It's there in the resources, but basically we've got a flying weight going around in a circle being held up by 0.09 kilogram mass Q. And what we've got to do is we've got to come up with that expression that V equals 2 pi r over T. So from first principles, V equals the distance over time, and the distance is equal to the circumference. I'm being very, very ginger because we've been thrown off. The circumference is the distance that of one complete circle that the object takes, circumference. divided by the time for one whole period. So that would be period, big T. And circumference is given by 2 pi r, where the r here is capital R over big T period. Okay, moving on. I mean, there are other ways of doing that, but we'll just focus on just one. And if you want to read the mark scheme for other ways that you would prefer to do, you can do that. You still get your marks. It's still valid. Okay, so complete the table. So basically, we've changed R and we've timed for 10 oscillations. So first of all, we've got to work out the time period. So we just divide that by 10, and we'll keep it to 2 significant figures here. We won't add another one at all the way down. And then what we've got to do is find V using your equation, V equals 2 pi R over T. So putting in 0.5 and 0.47, we can get an answer for example, 0.684, which you would round to 6.684, round it to 3 significant figures. You could leave it as 2 significant figures, but you can go to one more. So 6.68 is how you would leave it. And then if you square that, I would keep it to 3 significant figures, so 4 to 4.6. Now, however many significant figures you settle on, 2 or 3 significant figures will give you your marks. Just make sure it's the same all the way down the column. So this one will all be 2 significant figures, and this one, then when you work it out, 7.25, 7.85, 8.38. Now be careful when you're rounding, round it correctly. Be careful also if you've got something left in your calculator, because they're assuming that you're going to do 7.25 squared, not what's on your calculator all squared. You'll get a slightly different number, and it might affect your results. So 52.6. So keep to the same number of significant figures all the way down, consistent with what you've got, or one more. Write an equation relating the centripetal force to V and R. So the centripetal force is given by mv squared upon ma. Is the force is given by mass times acceleration. Oh no, hold on. I'll need that for the next one. Sorry. Centripetal force is given by mv squared upon r. But we know that r is equal to big R, and we know that the mass that's circling around is given by 0.010 kilograms from the diagram. So we can slot that in because we want to find the force in relation to V and R. So the centripetal force can be given by 0.010 times by V squared over big R. Hence, by using the equation for the forces, so the centripetal force is equal to, yes, we know it as 0.01 times V squared over R, but that is been given by in its force, a real force, which is the weight of the mass hanging down, which is equal to mg. And the mass there is 0.090, and that's what's hanging down from in the diagram. And that equals 0.010, 0.09 G, not kilograms. I don't mean that. I mean G. G equals 0.01 times V squared over R. Now let's just rearrange it to get V squared on its own. So V squared equals, bring R up, bring 0.01 down, so 0.090 times by G over 0.010 times by R. So, of course, 0.01 goes into 0.099 times. So we've got 9GR equals V squared. And this is something else as well. Show all your working and show your cancellings out and things so that you can fully get credited for what you do. Now we're going to have to plot a graph. Now, plotting graphs is exactly the same thing if you had to do an experiment. You get your marks for the choice of the axes, for spreading the axes out over the whole graph grid available, for plotting your points, for drawing your line of best fit. And whereas we don't encourage the use of these little things here, because you can use the whole graph grid, we can kind of like start. So, for example, we're going to put R along here. So put meters in brackets or with a slash. We're going to put V squared here. So remember, it's not just meters per second, but it's all of that squared. All right. And if you've got it, they've given it to you in the table. So they're going to expect you to get this right here and transfer it correctly. So R starts at 0.5 and goes all the way up to 0.9. So you can either start it here at 0.4 or 0.5, but just as you, so 0.5, 0.6, no, 0.5, will this do it? 0.6, 0.7, 0.8, 0.9, because my first one is 0.9. It should do it. Am I doing the right thing? I'm thinking I am doing the right thing. Yeah. Okay. But I'm a little bit worried because you see, if I go 0.5 to 0.9, am I doing something wrong? No, I'm all right. Yes. Okay. I'm fine. Okay. That's okay, because you see, what you've got to look at is I know that the first point is going to be here, 0.4 to 0.9. And as long as that spreads out over more than half the graph grid, I'll get my mark. Okay, and then V squared, I want to go from 40 up to 80. So I could start it here at 40, here, 60, 70, 80, okay, and 90. And 44. So it's going to be, in between this one and this one here. So that's more than half the graph grid. So I know that my plotting is going to be all right. And you have to be able to plot these points to the nearest half a small square and check every single one of them. And if you're running out of time, plot your points, look back at them, draw your line of best fit, and just check the one that is way out, that looks a little bit far out from the line of best fit, and then go back and even go and check a calculation in your table if you need to. Okay, so I think I'll move on from that because the marking guidance is there. You've got the axes, you've got the labeling, you've got the sizing, no irregular scales. And I could go on all day about graphs, as James will know. I won't. I'll carry on. So now what we've got is I think I've jumped on somewhere. Oh no, I'm all right. So V squared. So we've got the equation V squared equals 9GR. And we want to determine a value of G. And what you want to do is, using the graph that you've drawn, you answer these next few questions. So we relate this to y equals mx. We've got on the y-axis V squared, on the x-axis we've got r, which means that our gradient m, it gives us 9g. So if I work out my gradient, divide it by 9, I get my value of g. Now, when we are doing a graph, let's just go over to this one here, since we've got one already. Just take the biggest possible triangle and label up the read-offs, because that is what you're getting marked 0.4. So take the whole lot, use a ruler, don't do what I'm doing, use a ruler. Don't use these here because you can read off from the axes here. So if this is kind of like 45 here, this will be 35 here. And this is 0.4 here, this will be 0.9, and it looks close to 0.96 here if I follow it up. But use a ruler and show your read-offs. This will be 85 here, I think, 85. And then transfer those gradient markings. Oh, where are you going? Why can't I go up? Why can't I go up? Let's try and go down. Okay, yeah. Use the gradient markings to do dy by dx. You know, you're doing this part divided by this part. Try and not get confused and do dx by dy. And then just divide the gradient by 9 and you get the value for the gradient. But look here, they snuck this in because, you know, usually you don't need a unit on the gradient, but you do for the value of g, you see. So you've got to follow through and realize that the unit will be meters seconds minus 2. Now, fortunately for you, you didn't have to work anything out in terms of units because they've already got them from the table, so you can take them across to the graph and then you can work it out because it's meters squared seconds minus 2 here, it's meters here. So when you put it into the equation, then one of the m's cancels to give you meters per second squared. Or you might just know that the unit for g is meters per second squared. So suggest a way in which the experiment can be improved. There's many, many different ways that you can improve it. You could have repeated values of r. You could have done more rotations. You could have, you know, used a video with a timer in the shot to take the readings to make the timing more accurate. It's interesting that here they say they accept repeat readings. In another exam, they might not. Okay, so say what you want to repeat. You might want to increase the radius, which gives us a higher period, so the percentage uncertainty in that timing is a lot smaller. Okay, all right, moving on. I will see now where we go. I think we've got one more question to do. Okay, so this is a pendulum one, and the reason why I kind of focused on this one and not done the ones previous to this is because of this phenomena of sine theta is roughly equal to theta for small angles, and only if theta is used in radians. And I think this needs touching on because WJC do like to kind of like bring this up. And if you aren't familiar with this mathematically, you need to make yourself aware of this. So there's two forces acting on the mass there. There's the tension in the string, okay, and then there's the weight acting down, okay, the weight or the gravitational pull acting down. Okay, now we've got to consider these forces and show that the resultant force component on the mass along the arc is minus mg sine theta. Right, so what we're meaning is this component here, okay? So a resultant force in this direction. Now you can see that this is a tangent. So the first point to make is that the tension has no component at all because that is at right angles to the resultant force, at right angles to resultant force. Okay, so we don't have to do anything with the tension at all. Now we have to look at mg. And mg, if this is subtended at an angle theta, then this here is angle theta. And now I always say to my guys, if you're going away from the angle, so if I've got mg here, okay, and I've got and I want to get the component of that tangentially as opposed to you know, in the same direction as the tension. And this is theta. Can I just check? Yeah, this is theta here. So this will be theta here because this is parallel with this one and this is parallel with this one. And what I want to find is I want to find this part here, the tangential component of mg. So if I go away from this angle, sine theta. So I automatically say that this is mg sine theta. If I had to go through it, then it would be through the angle, it would be mg cos theta. But if you want to be strict about this, okay, this is the opposite side that I want to find. This is the hypotenuse, okay, which we've got, which is mg. And then sine theta is equal to opposite divided by the hypotenuse, which is equal to the opposite bit, which is what I'm trying to get, divided by mg. So that is mg sine theta. Now, that's not the whole story, because if I take in this direction, it being positive, the displacement from that position, that equilibrium position at s equals 0, and s in this direction is positive, then it's acting in the opposite direction to that. So that's why we put a negative in front. So this is for the fact that it's acting in opposite direction to s. Direction to s, and back towards the equilibrium position as opposed to away from it to the right. Okay, so moving on, I think that answers that, because what we do now is we do minus mg sine theta plus 0 equals the resultant force. So it's just equal to minus mg sine theta. And then the clever stuff comes into this bit now. All right, if the oscillation is so small that sine theta is roughly equal to theta, show in clear steps that the acceleration is given by that g minus gs over L. Now, okay, so we know resultant force equals mass times acceleration, so that the resultant force divided by the mass is equal to the acceleration. But we've just been told that the acceleration is equal to minus mg sine theta. So if we divide that by the resultant force divided by mass equals acceleration. So the resultant force divided by the mass, cancel the masses out, equals minus g sine theta. But sine theta, but since we have this mathematical phenomena that if we're working in radians, sine theta is roughly equal to theta as long as you are using radians. We can say equals minus g theta. But what is theta at the end of the day? Theta is equal to the angular displacement, and the angular displacement is given by the arc length divided by, that is given by s, divided by the radius r. Okay, so we can substitute for that. So therefore, we've got A equals minus g s over r. Oh, but r is equal to the length of the pendulum. So we can say A equals minus g s over L. Now, discuss whether the equation satisfies the definition of simple harmonic motion. Well, for simple harmonic motion, the acceleration is proportional to the negative of the displacement. Now, this could be displacement as an angular displacement, or we could say that it's proportional to the displacement from the equilibrium position, i.e. the arc length, or we could say in terms of x. All right, i.e. the linear distance as opposed to the arc length from the equilibrium position. And the fact is that as long as you've got this, you know, you can say that because you've got A is equal to minus GS over L, you've got this A, you've got this S, you've got this negativity here, and so you can say A is proportional to the minus displacement. In simple harmonic motion, you've got to have this negative sign because the displacement is in the opposite direction to the acceleration. So the acceleration is always going back to the equilibrium position, whereas x is going outwards. And so it's always in the opposite direction, but it is directly proportional to it, so that if the displacement kind of increases, then the acceleration back towards the center will increase. All right, if one doubles, the other will double. Okay, so yes, it does, but you've got to say that, yes, it does, and you've got to explain it, and it asks you to discuss it. So it's not good enough for me just to put all of that there. You've really got to kind of like be very kind of like specific and say acceleration is proportional to S, all right, from a fixed position and opposite in direction. So therefore it obeys SHM. You've got to kind of like link it back. Okay, right, so a small mass oscillates. These are lovely little equations, really nice on the last bit of the kind of like questions for Unit 3 before you get onto the synoptic one, which is worth 20 marks, to have these kind of like little equations in. So if a small mass oscillates of a length 1.2 meters, and T equals 2 pi root L over G, and then you're just going to put L equals 1.2 and substitute it in, and you get 2.20 seconds. And then frequency, you know, is the inverse of the period, i.e. it's the number of oscillations per second, vibrations per second. So if you've got the time, just 1 over the time, get the reciprocal, and 0.455 hertz, because all we did was 1 divided by 2.2. What a gift on those last 3 marks there. Now, lastly, before I stop, if the maximum displacement angle is 0.067 radians, justify the use of simple harmonic motion in part B, part 1. So what we're saying is that the theta max, okay, is in radians, 0.067 radians. Okay, and that is equal to sine theta max. And if we actually do this sine of 0.067 using our radians function on the calculator, we get 0.06695. Sure enough, it's very similar. All right, and so since we can say that theta max is equal to sine theta max, then this must be true for all values, because don't forget, this is the maximum angle that we are going to be using. So all the other angles, then it will all be true. All angles. Okay, because they're all under theta max, between 0 and theta max. So therefore, we can say that sine theta is equal to theta for all values and approximately holds. Therefore, SHM. Okay, now I think I'm going to stop there, and I'm going to stop sharing, and I'm hoping my colleague is still there, and we're going to stop this session. And thank you for joining us.
I'm still here, Jane.
Oh.
Yeah, thank you for that, and yeah, we hope that this part, well, Unit 3 is a little bit clearer for having gone through a paper. So goodbye, everyone.
Goodbye, everybody, and yeah, we just haven't done synoptic, and that would have taken another 20 minutes to do that. So enjoy your evening, and thank you for listening. Goodbye.
Bye-bye.